Hi, we're back. Last time, if you remember, I've explained two very important theorems. Miyakawa's and Kawasaki's theorem. So, now that we have armed ourselves with the basic theory, we can return to our simple examples and try to develop a proper crease pattern. Let's try. In previous episodes, using a very simple example, we have managed to define all creases, getting something that resembles a crease pattern. As you can see, all creases or folds are here. What we have to do now is to define their orientation, that is, for all the creases we suppose to define if they are a valley or a mountain. This is what we are gonna do. We are first gonna define the orientation of axial creases. This is the easiest way, believe me. This isn't supposed to be hard, since we haven't yet used more complicated origami elements, such as level shifters. So, since there are no level shifters, we can be pretty sure that every other axial crease has to be a valley or a mountain. Therefore, the only thing we need to do is to define the orientation of the first axial crease. The rest should be easy. My suggestion is to begin with the paper edge and to declare it a valley. Frankly speaking, we could have declared an edge as a mountain, and everything would be fine too, except that everything would look as if we had turned the paper upside down. Nothing more than that. Nevertheless, in this example we'll assume an edge is a valley. So, if an edge is a valley, then we can define the orientation of all the other axial creases, because axial creases, being parallel to one another, are always of the opposite orientation in relation to one another. To put it simply, if the first axial crease, in this case the paper edge, is a valley, the next one is a mountain, the third one again is a valley, and so on. I hope you understand the concept. All the valleys, as you can see, are blue, while all the mountains are red. This is our convention. Also, please note that the axial crease never changes its orientation, regardless of how many times it changes direction. I hope this is clear. Now that we have defined the orientation of all axial creases, we have to do the same with ridge creases. But before we do, let's establish some basic rules, or if you like, guidelines. I've used the word guidelines on purpose because if we apply these rules, we will get a proper ridge crease orientation. But that orientation is by no means the only possible. Or to put it simply, the rules I am about to share with you are not universal. There are other possibilities too. Nevertheless, we will stick to these rules since they will provide us with a procedure that is the simplest one and as such, most widely used. So, the rules or guidelines, if you prefer to call them so, are as follows. First, whenever a ridge crease intersects an axial crease, it changes orientation, meaning, on one side of the axial crease, the ridge crease has to be a valley and on the other side a mountain. Second, whenever a ridge crease changes direction, its orientation stays the same. Let me show you these rules on a proper example. Look at this vortex. At this vertex, the ridge crease should change orientation. From a valley it should change into a mountain. But it is fair to ask which side is a valley and which a mountain. The general rule is as follows. Whenever the angle between two axial creases is less than 180 degrees, a ridge crease of the opposite orientation should be in between. This is logical. In between two adjacent valleys there should be a mountain, and in between two adjacent mountains, there should be a valley. So, if axial creases are red, then this segment in between must be blue. Of course, if we want to follow Miyakawa's theorem, the opposite ridge crease should be red. I hope you understand this rule. Every second segment of any ridge crease has to be differently oriented. However, there is an exception to this. Let's take a look at this vertex over here, at the bottom of a paper. This situation is a little bit different. Look what's going on with the ridge crease. The ridge crease changes direction. So, in this case we should implement the second rule, meaning the orientation stays the same. This is very important to remember. These two rules will help you set the orientation of the entire ridge crease in one go. Take a good look at this ridge crease, here marked in orange. This ridge crease goes over the entire crease pattern. Now, let's set its orientation, one segment at a time. All we need to do is to define the orientation of one initial segment. For example, this one in the middle. It obviously has to be a valley since it is in between two adjacent mountains. I hope this is clear. After that, everything is quite simple. Every other segment has a different orientation, except when the ridge crease changes direction. In that case, the orientation stays the same. Do you see how orientation does not change when the ridge crease changes direction? It is a valley both before and after the direction change. So, using these two simple rules, we can define orientation of all ridge creases. I hope these rules are clear. Now, what is left is to go back and to define orientation of our first ridge crease. You see, quite simple. Since we've managed to define the orientation of all ridge and axial creases, we can now go on and deal with hinge creases. It is these yellow marked lines. Have you noticed that, when we tried to define orientation of both axial and ridge creases, we never bothered to see what was going on with hinge creases? We acted as if hinge creases did not exist. This is because hinge creases most often really do not exist. To be more precise, only a part of lines defined as the hinge crease, here marked in yellow, actually do appear on the final crease pattern. Because of this, many have a problem recognizing polygons on a fully developed crease pattern. Simply because hinge creases, lines that define polygons, are only partially visible. So, the question is, when do hinge creases appear, at least partially? Well, they appear in a vertex that wouldn't otherwise satisfy Miyakawa's theorem. In other words, we are adding hinge creases only to ensure the flat foldability of a model. With this in mind, let's analyze that kind of vortexes. Do you see any of them? There are 5 such vertexes. Do you see them? For instance, we can count the number of valleys and mountains in this vertex in upper left corner. We can see that the difference between the number of mountain and valley folds is 3, not 2. We have 3 mountains and no valleys at all. So, we obviously need 1 additional valley at that vertex. But the question is, where should we add that valley? The answer is quite simple. We can add it anywhere, in any direction, as long as it is perpendicular to the axial creases. Remember that. It always has to be perpendicular to the axial creases. I don't know if you have noticed, but all available directions are in line with hinge creases. Generally speaking, what we're gonna choose is up to us. My suggestion is to choose a direction that will lead a hinge crease down the shortest way toward the paper edge. So, if we choose to go straight up, then we have to add only 1 valley, 1 unit long, and Miyakawa's theorem will be satisfied. The same would be the case if we decided to add an additional valley to the left. But if we choose to go right and add an additional fold there, things will become a little bit more complicated. If we want to do so, we will have to respect some rules. So here they are. We have to keep drawing lines or creases until A. We reach a vertex that has the same problem. B. We hit a ridge crease. Once an axial crease hits a ridge crease, the axial crease goes over it, but in doing so, necessarily flips over its direction, or in layman's terms, the direction it has after hitting the ridge crease reflects the direction it had before having hit it. And C. It goes out of a paper. It is probably best to show you these rules on an example. So, if we choose the third option, that is if we decide to go right, then we have to draw lines until we reach a vertex with the identical problem. A vertex that also does not satisfy Miyakawa's theorem. It's this vertex here. This is where the line or the crease ends. Please note that drawing a straight crease was possible here because the new crease didn't encounter a ridge crease on its path. So now, since we have a new crease, we need to define its orientation. It would obviously be best if we would define the whole crease as a valley and color it in blue. This way the problems in both vortexes would be solved, which is more than fine. But doing this would cause the same kind of problem in this vertex in between. If we just think about it a little bit, we will soon realize that this problem can be solved very easily. So, what has to be done is to change the orientation of this upper vertical crease. And that's it. As you can see, the solution is a little bit different, but still quite simple. Finally, to make things more interesting, let's take a look at an example where the new crease hits the ridge crease. Let's analyze this vertex here in the lower right part of the paper. You probably realize that this time 2 additional mountains are needed for Miyakawa's theorem to be satisfied. In this case too, it would be favorable to draw 2 creases straight to the paper edges. But for the sake of argument, let's try to draw 1 crease straight up. So, we are going to keep drawing lines or creases straight up until we hit a ridge crease. See? Now, a crease has to turn left. It flips over its direction after having hit the ridge crease and then goes out of the paper. And this is it. The only thing left to be done is to define the orientation for these two creases. It's easy with the crease that went down. The first segment has to be a mountain and the second a valley. It is self-explanatory. The second crease is as easy as a first one. The only thing we need to take care of is to ensure that Miyakawa's theorem is satisfied in every vertex. Simple as that. What is left is to solve flat foldability problems at these two vortexes on the right. This shouldn't be hard since we know all the rules. However, let's do it in the easiest way, meaning let's add hinge creases straight toward the paper edge. And that's it. Now, you are probably asking yourself what's the catch? Why are hinge creases visible only when they supposed to ensure flat foldability? Okay, let's try to explain this using our simple example. Here we have a paper with a complete crease pattern. To make this example as easy as possible, all hinge creases are defined in the easiest way. Meaning, all hinge creases were drawn straight toward paper edges. Now we can fold our base and flatten it into a single plane. Okay, now let's look at this flap for instance. Do you see a hinge crease? There is one on the inner side of the flap. On the outer side there is no hinge crease at all. How so? Well, if you think about it, it's quite logical. You see, if we flatten the base like this, on the outer side of the flap a crease will disappear. Do you see that? The paper is fully flat. I can even unfold the base to show you that outer hinge crease really doesn't exist on the crease pattern. Can you see the polygon that forms our flap? Do you see that only a part of the hinge crease is there? The rest doesn't exist. I hope you can understand what I'm explaining. We can look at the other flaps, too. For example, this one. This one has hinge creases on both sides. Can you see them? Here is one and here is yet another. But if we take a look inside, we will see that there's no hinge crease inside. We have two hinge creases on the sides, but there is no hinge crease in between. Why am I showing you this? Well, I'd like you to be aware of the fact that there is a difference between hinge creases that exist on a fully developed crease pattern and real hinge creases on a fully folded model. You see, this flap can rotate in any direction, so obviously the hinge crease exists on both sides. But when we are looking at a crease pattern, we always have to bear in mind that a crease pattern design is very much influenced by the rules related to flat foldability. Therefore, not all hinge creases exist on a crease pattern, since, strictly speaking, when a model is completely flattened, some of the hinge creases will disappear. To be sure you fully understand this, let's look at our model from a different angle. For example, this is the same base, but this time one of the larger flaps is rotated into the opposite direction. As you can see, the base is flattened again. Do you see it? So, the base is still completely flat foldable. The only difference is that hinge creases appear in different places. You can see that the hinge crease now appears here, even though it hasn't existed there before. Furthermore, the hinge crease between two larger flaps has disappeared. To make things even more understandable, let's unfold the base and have a good look at the crease pattern. Do you see where hinge creases are now? The crease pattern is a little bit different, but the difference is only due to the fact that we turned the flap into the opposite direction. Nevertheless, everything is still in line with the basic rules. Again, I hope you understand the idea. Even though hinge creases exist around every flap, and thus we can easily rotate them, when we are designing a crease pattern, some of the hinge creases are due to the flat foldability restrictions left out. They are simply not drawn. This is very confusing for many. They have a problem seeing polygons simply because they cannot see all the hinge creases that define them. I hope you're not gonna be among them. Just assume where those polygons are by looking at ridge creases. Remember this. It's ridge creases that will show you where polygons are. But we will talk about this in the next episode. Then we will see how much you have learned so far and how much you really understand. In the meantime, on our example, try to find out all combinations of hinge creases. Of course, without breaking flat foldability rules. You can download the answers using the links below, but before you do, try to find a solution by yourself. You will find it useful. In the meantime, take good care and see you in the next episode.